If we need to map a free semigroup into multiple target semigroups, say S1, S2, and so on, then it would require many extractor functions with this type signature. Each extractor function will have to convert the generating element Z of the free semigroup into a specific semigroup S1, S2, and so on. We can refactor these extractors into evidence of a type class constraint. So instead of saying we have a semigroup S and we have this function for that semigroup, we would say we have a semigroup S that additionally has a type class constraint, and so we define a new type class, let's call it XZ, for extracting from Z, and it has a single method of this type signature. Then we can refactor the run function into this form. It will be now parameterized by a semigroup S that additionally to the semigroup type class also has an extract Z type class instance, and that would mean we would have an evidence and value of this type which would contain this function. So that's very similar to what we had before when we had the run method that had an argument containing the extract. Now we will have no such argument. We will just have an argument specifying the free semigroup value, and additionally we will have a type class constraint which in Scala is translated into an implicit argument of the type exz of semigroup, which will just contain this extract function. So far this is a refactoring that doesn't seem to bring a lot of benefit, except that now this code is going to be completely the same for all extractors, and we just need to define different extractor type classes for different semigroups. So another refactoring that will follow from this is found if we look at the structure of this run function. So what does it do? It translates the free semigroup value into a value of the specific semigroup S by pattern matching on the case classes from the free semigroup. And the free semigroup has two case classes, the wrap and the combine case class. What the run does is that it replaces these case classes by some fixed functions. And these fixed functions are parameterized by a semigroup having this extractor constraint. So all we have done is first we have created a value of a free semigroup, which will be some case classes, and then we just translate these case classes mechanically into these fixed functions. So the main idea of what is called the Church encoding is to represent the free semigroup directly by these functions. Just skip the case classes. All these case classes do is to denote what needs to be done, what these functions will have to do when we run the free value. So instead of representing a free semigroup through these case classes, represented directly through these pieces of the run function. In other words, instead of saying that the free semigroup value is of type wrap, we say it is equal to this function, which will be parameterized by this semigroup S with two type class constraints. So here's what will happen if we do that. We will have two functions. So one would be the combining function, and one would be the wrapping function. But the combining function actually is defined in the semigroup S. It is not something we define. So really, we just need to define the wrapping function. So this wrapping function will be this part of the run, and the combining function is already defined because the plus operation is part of the semigroup type class. So the definition of the free semigroup just becomes the definition of a wrap function, which is parameterized again by this. We don't need the semigroup constraint right now for this function. We could have written it, but we wouldn't have used it. And then suppose we want to define a value x of type free semigroup, which would be, say, a combination of wrapping 1 and wrapping 2. Instead of doing that, we just write down this. So note, these are values of the free semigroup. And these values are now defs, because they're not vals, they're defs, because they're actually functions parameterized by a type parameter and having implicit arguments, so they cannot really be vals anymore because they're parameterized by a type parameter. That's another difference. So now we have encoded this x. So this x is basically a function that already runs. It's waiting for you to give it a semigroup S, but once you give it, then it will run, and all the implicit arguments will be substituted, and you will have a value in your semigroup. But until then, you have defined it, and it's waiting for you to run it. So this is then the encoding of the free semigroup using functions, using directly pieces of the run function. So we don't need a run function anymore. We already encode values of the free semigroup through the pieces of the run function that would be run in the previous encoding. So the previous encoding is a tree encoding, or the expression tree encoding. This encoding is called the church encoding. Let's look at the type of x explicitly. Let's drop all this syntax. What is a type of x? Well, first of all, it's parameterized by a semigroup type S. And so this is a function that will work for any type S. So let's write it down explicitly as a universal quantifier, which will be read for all S. So for all S, we have a function that takes the extract Z type class evidence, which is a function of type Z to S. It takes the semigroup class evidence, type class evidence, which is this method, and it produces a value of S. So in other words, it is this function, which is parameterized by type S. So this should work for every S. And we want to write this explicitly using the universal quantifier. Now we can simplify this type using an identity that the product of these two functions is equivalent to a single function from disjunction of Z and S times S to S. So now this type, which is equivalent to this type, which is equivalent to this is the church encoding of the free semigroup over Z, or free semigroup generated by a type Z. I call this church encoding for reasons that I will explain. But look at this type signature. This type signature looks a little bit like a continuation monad. Continuation monad would have this type. Now we have this and then these two nested functions. They're very similar to a continuation monad, but it isn't really that. It's not really a continuation monad because of this quantified type. The continuation monad has a fixed result type R. It is not quantified over that type. It is not parametrized by that type, and does not have for all R in front of this. But we do have for all S because this is our type parameter in the function. So each value of the free semigroup is a function parameterized by an arbitrary S. S being a concrete, non-free semigroup, or perhaps another free semigroup, but eventually it must be a non-free semigroup in order to get any values out of this. Non-free actual useful values. So that's the type. Now, there is a theorem in the type theory, which is that this type expression is equivalent to just the type A. I will present a derivation of this somewhat informally, but this is the basic fact that is at the basis of the entire idea of the church encoding. What I call the church encoding of a type A is this type expression. So whatever type A is, you can just say I have a type A, or you can say I have this function parameterized by an arbitrary x with this type signature. That's equivalent to having a type A. So I call this the church encoding of the type A. And so unlike the continuation monad, the presence of the universal quantifier makes this function fully generic in X, and it becomes like a natural transformation between this functor and this identity functor. So this is a reader functor with type A being read and X is the parameter, and this is the identity functor with X as the parameter. So this is resembling a natural transformation between these two functors. And we know that if this is a function with fully parametric code, in other words, code that does not use any type information about X, then this will actually be a natural transformation. There is, however, a bit of difficulty in understanding how to work with church-encoded types. They're complicated. There's this function whose argument is again a function and it's parameterized over arbitrary x. It's actually not easy to reason about such types. So in order to develop intuition, let us consider a simpler example where we take a disjunction type, just an ordinary disjunction type, not a functor, nothing like that, just an ordinary disjunction of types P and Q. And let's work with its church encoding. So by definition, the church encoding of this type is this type expression. Now we can simplify this because it's a disjunction in a function argument, and this is equivalent to a product of two functions from P to X and from q to x, and this is equivalent to a curried function with this type. So far I have done nothing but I have equivalently transformed this type into this for convenience. Now in Scala, in order to implement such things, I have to hide this type parameter somehow. I cannot have a type, so I need to have a type that has inside of it a def with type parameter. So in order to hide it, I have this Scala code, which is the usual pattern for putting a universally quantified value into Scala, because Scala does not have universally quantified values. It must be a def, as I did before. Now this is not very convenient. You want to have a val with universal quantification inside. So in order to do that, you define a trait. Let's call this trait disjunction. It's going to be church-encoded disjunction. P and Q are going to be just parameters for it. I didn't necessarily have to do it this way. Importantly, this trait has a method inside that is parameterized by x, and this x is not one of these type parameters. So this type parameter x is hidden inside the trait in this way as a method of the trait. And when that happens, when a type parameterized function is a method of the trait, it means that you can call this method with any type parameter x. So in this way, it implements the universally quantified type x. And it's very easy to just write down this function signature like this. So how can we define values of this type? So for example, we define left. Given some value of type p, we want to define the left part of the disjunction. We need to create a value of type disjunction. So in Scala, this would be creating a new anonymous class by extending this trait and implementing the method run. So this is Scala's boilerplate for hiding the universal quantifier. But then we just need to implement this function, which is easy. We need to return x. We have the two functions, p to x and q to x, and we have a p. So how do we return x? We just call this function on the p. So in this way we implement the left. We also implement the right. In this way we can create values of this type now quite easily. So suppose that this is a value of this type. How can we implement a case expression? Well, we can just call the run method on two functions like this, and that would be actually the case expression. So the result would be of type x, because that's the result of the run. So in this way we program with disjunctions in the church encoding. And note that this would work in any programming language that has nameless functions. The programming language does not need to have disjunction types built in. So all we need to do is we need to create this construction, which does not have any disjunctions inside. Now this does. So this I would not be able to implement in a programming language that doesn't have disjunctions. But this I can implement in such a programming language. And so actually I have heard that people have used this trick, the church encoding, for implementing disjunctions in JavaScript. The Go language also comes to mind as a very primitive type system. And I'm not sure how, but with generics it would certainly be able to implement disjunction types. Java could do this too. So, general recipe for church encoding is that you need to hide your universal quantifier. So you create a trait with a method which I will always call run in this tutorial. This method has an argument, which is this continuation-like function, or this function, maybe several of them, maybe a product of them if you have a disjunction. And then you can also think about making it more convenient. So if you have a lot of things here, not just one function, but a lot of parts of the disjunction, this could be cumbersome. So you could split it into products, a product of functions. And then you could say this is a value of some type. So you could even do a trait or a case class parameterized by x containing just this argument of the church encoding, just for convenience. And this is specifically very convenient with disjunctions because you could just define like this. Instead of defining a run method with this type signature, you could define it as a function from ex of x to x. And so this is actually much easier to use with languages such as Java or JavaScript, where you have objects with methods, but you do not have disjunctions. Now, notice that case expression, which replaces pattern matching for disjunctions, is actually consisting of running this function. So the church encoding of a type is a function, and calling that function means running. So just like in the free type constructions, when you interpret the free value, or a DSL, or your interpreter runs, you get some final value. That's in the church encoding means you call this function and get your final result. The church encoding, in some sense, encodes your DSL or your operations or your program, your declarative program, encodes in terms of pieces of the interpreter that are necessary to run it. And so pattern matching is impossible on functions. You cannot determine whether this function uses its argument or not, for example, by any kind of pattern matching on this function value. You cannot do that. The only thing you can do is to run this function. So one deficiency of church encoded types is that they have to be run in order to pattern match. You cannot pattern match, say, on a disjunction without actually having some kind of result type, some kind of target x, and putting that x in there, putting the extractors in there, and running this function. Now, certainly, you could be clever, and your x could be another church encoded something else, certainly, or non-church encoded something else. You could very easily convert this back into the ordinary disjunction type, and then you could pattern match on that. But in order to convert this to anything, you have to run it. So church encoding has certain advantages. It is easier to work with if you have many targets, and we will see other advantages of the church encoding. It does have also disadvantages, and I will talk about them. But one disadvantage we see right away is that pattern matching is impossible until you run, or unless you actually run your church encoded value. So let us see how the church encoding works. So why is this type equivalent to the type A? So let's just consider this very simple church encoding of a fixed type A, which will be implemented like this. So in order to show equivalence between the church encoding and the type A, we need to present isomorphism between the types, which is a pair of functions from A to the church encoding and from the church encoding back to A. And we need to show that these functions are inverses of each other, so that the composition of these two functions in every order is identity. So if we have a value of A, how do we get a value of church encoded A? Well, if we have a value of A, then in order to produce this, we take this argument, which is a function of A, and apply that function to the value of A that we have. The result will be a value of X, which we return. So that is the code. We just apply this given function, or the continuation argument, if you will, to the given value of A. So that is in one direction. In the other direction, in order to extract A out of this, we can call, well, the only thing we can do, obviously, on this value, which is a function, is to call that function. On which argument and with which type X, that is our choice. So we call this function by calling run with type X equal to A. So like this. And on an argument, which is identity function from A to A, the result would be some A. So that's our second converter, C to A, the church encoded to direct type. So it remains to show that these functions are inverses of each other. So how do we do that? Let's think about how could it be that we have a value of this type. For any x, given this function, we're able to produce a value of x. Now, if I am able to produce a value of an arbitrary type x, and I don't know anything about that type, the only way I can do that is by using this function somehow. And this function needs to be called to produce an x on some value of A. So unless I have a value of A, I can't possibly have this. So this is the intuition that explains why this type is equivalent to A. The only way of having a value of this type is to have some value of A. Now this value, what if I had two different values of A? Well, the problem is I could only use one of these two values, because I'm supposed to produce this, which has a universally quantified x, and I'm not supposed to look at x. So this is supposed to be generic in x. So I could not, for example, check whether x is integer, then I use one value of A. If x is not integer, then I use another value of A. That is not allowed by this type. This type is fully generic in x, and so I am not allowed to use any specific information about what the type x might be. I could not write code like that. I mean, I can write code like this in Scala, of course. But that is not what this type is. This type says this is a fully generic function, which is a natural transformation from this functor to this functor. I'm not allowed to look at the code of x, at the type of x. I'm not allowed to use reflection, for instance, or any other information about the type of x, or the value of anything. I'm supposed to be completely generic. So, if I had many values of a at my disposal, I would be forced to choose one of them for all x, and to use that one value of a in order to create this thing for all x. In other words, the only way to have a value of this type is to have a fixed value of a. And then this is how I'm forced to implement a value of this type. So that's intuition. Now I would like to be more formal and show that for any church-encoded value, ch, if I first convert it to a using this converter, and then I convert it back to ch, then I have the same ch as I started with. But what does it mean I have the same ch? Ch is a function. So this function must be equal to that function. Now, equality of functions means if I substitute some argument into that function, I get the same value as a result by applying this side and this side. So let's apply both sides to some function f of type a to x. And then we can simplify this. So what is the ch run of f? Is on the left-hand side. On the right-hand side is this run of f. Now this run of f, we can see what that is. It is a continuation of a, which means it is an f, because the continuation is going to be f. The argument of run is going to be f. So f of this. Now, substitute the definition of C to A. It is this. And f of that, so ch.run of A to A. Now, we cannot really simplify this anymore because we don't know what ch.run does. Ch is an arbitrary given value of this type. So we don't really know what it does when we call it on A to A. But if we look carefully at this equation, so we are now required to prove that this is equal to that. Looking carefully at this equation, we find that this is the condition of naturality of the function chrun as a transformation between the reader functor and the identity functor applied at type x. This is the naturality condition. Here is how I can illustrate this using a type diagram. A naturality condition means that if we do an f-map, so we have one functor on the left, another functor on the right, we have a natural transformation between them. If we now f-map with some function on the left, and we f-map with the same function on the right, the diagram should commute. And this is precisely the equation that we have written here. The run of f is precisely that f, sorry, I'm confused. It is this direction first. The left-hand side is this direction. This is the run of f. And the right-hand side is this direction. First, you run of identity, and then you apply f to that. So the left-hand side corresponds to this direction on the diagram, and the right-hand side corresponds to that direction on the diagram. Commutativity of the diagram is therefore exactly the same as this equation. So, in other words, we have shown that this function will be equal to that function as long as we demand that this is a natural transformation. So this code must be fully generic. It should not use any type information about x. And the counterexample would be looking at the type of x and using different values of a to create a to c here. So calling this on different values of a depending on what x is. So we could write this code in Scala, but this would not be a natural transformation. The other direction is easy to verify if we just substitute the code c to a of a to c of a. C to a is this, and then a to c of a has a run function, and then you have identity applied to a, and that's a. So in this way we can show more formally that this type, the church-encoded a, is actually equivalent to the type A, as long as we understand that this must be fully generic code and, in other words, a natural transformation between these two functors. And another property of the church encoding is that since it is built up from parts of the run method of some type class, usually, it will automatically satisfy the laws of that type class. Now this example, as well as this example, were not examples of type classes that I was going to church encode. This example was a type class that I church encoded, the free semigroup. And the property of the church encoding is that it will automatically satisfy the laws. And the reason is we know that laws will be satisfied after you run the type class, the free type class instance. This we already saw. And therefore, since our church encoding is basically functions that run, and the only way you can use them is to call these functions, then church encoding will satisfy laws automatically. In the same way as this function is equal to that function, which we verify by calling these functions, applying them to a specific arbitrary argument, a law for a type class means that you need to run the church encoding and then compare the results. And so since we know that the run method for free type classes satisfies the laws, it follows that the church encoding of a free type class will automatically satisfy the laws of the type class. So this is a very nice property of the church encoding. Let us look at the code of church encoding a free semigroup. Here we define the extraction as a type class, and then in order to define the free semigroup, we have very little work left to do. Unlike previous implementations where we have to first define case classes and so on, we don't define any case classes here. The wrap constructor is like this. And then we are ready, after this we have defined the extraction type class. We are ready to start working with semigroup values. Don't need any more preparation. So here is x and y. These are already values of the free semigroup. So here's a computation. We wrap 1, wrap 2, wrap 3, add them. That's it. We have now defined x and y. These are free semigroup values. No more ceremony. So this is another good thing about the church encoding, perhaps. In order to interpret, we don't need to define interpreters. These are already interpreters. Let's see how that works. We will interpret this free semigroup into string, which would have a standard semigroup instance. So let's define those. Standard semigroup instance for string. Now, in order to extract into string, we need to have an extractor. So let's make it available. So now string has a type class instance of the extractor type class. And we can run. That's it. That's how we run. We do need to specify the type parameter, but that's it. So we don't say, oh, run this with that extractor. All of that is implicit. And so if we have a lot of computations in our DSL, those computations are going to be more concise. Here is the code for implementing disjunction with some testing. Here's, for example, how we have a case expression. So x is a disjunction, which is left of ABC. And here we want to match on x. And we have the two possible cases, and that's how it works. So now we have seen the encodings of free type classes. Let's now look at examples and have more intuition about how these encodings actually work and what are the trade-offs in each of these encodings. The simplest type class that has type constructors is functor. Now, until now we were looking at semigroup or monoid. Now these are type classes for types. Functor is a type class for type constructors. Now for type constructors, things are a little more difficult, and there will be more syntax and more type notations. However, they're quite similar to non-constructor type classes. In very important ways, they are very similar. So keep in mind that free semigroup, free monoid, or free functor are basically applications of the same construction to different type classes. In order to construct a free functor, the first question we need to ask is what methods this type class requires. So there's one method. Let's look at this method. So the tree encoding of a free functor would have directly encoded this as a case class. Let's call it fmap. And it will also have a case class for wrapping a type constructor that we generate from. So to remind, the free functor type class needs to be generated by a type constructor. So we don't just have a free semigroup. We have a free semigroup generated by type Z. So we don't have a free functor. We have a free functor generated by a type constructor f. We need to start with some type constructor, which doesn't have to be a functor. It can be, but it doesn't have to be. So I call this free functor over f. Now, I introduce this notation, this bullet, in order to emphasize that f is a type constructor. It has a type argument here, which I'm not writing. I could write fa, but a is not known. A is an argument, so it's a type function, really. So I'm trying to find notation for type functions. So in Scala it will be like this, and I don't like this notation so much, but it's okay. But in my short notation, I right now found this to be a little better, more visual. So this is a type constructor f that waits to be given a type argument. So just like this in Scala. And so this is the tree encoding of a free functor. So I call this a tree encoding because this encodes an expression tree, unevaluated expression tree for a functor value. Now, what did I do in order to write this code? I basically did the wrapping. Now, a trait must be there. This is a Scala syntax for disjunction. So I need a disjunction. So one case class wraps a value of f of a, and the other case class wraps this. So it's going to denote the result of applying fmap to a free constructor. Note that this fmap has an extra type parameter because we extend f of a, so I have chosen the name z here. The result of fmap is f of a, so we extend f of a. But the arguments of this case class, or the parts of the case class, have a parameter z. It's an arbitrary fz, which is going to be this, the free functor of z, which we map with the function z to a. And the result is a free functor of a. So this type parameter z is hidden inside the type constructor. We extend ff of fa, not of z. So the z is not visible outside. So outside we will think this is a value of this type, but actually inside it has a z. Now this is a very interesting situation, that we have a case class parameterized by an extra type parameter, which is hidden from the outside type. And let us look a little in more detail about what it means to have such a type parameter. Let's consider a simpler example, simpler than all this, and write this code. So I declare a seal trait with a type parameter a, and inside it I have a case class that is parameterized by another type parameter z, and it has values that depend on z, but it extends q of a, so it hides the z from the outside type. Let's look at how this works. What if I wanted to construct a value of type q of a? How would I do that? Well, here's how. There's only this case class, so I have to use this case class. And I have to specify some other type for z. So let's specify string. And then I would have a value which has visible type q int, but actually inside it's hiding a string type. And it knows that it's hiding, it's parameterized, so it could have been another type. So when we have a value q of this type, we know that it is integer in this parameter, but we don't know what is this other parameter, z. We know that it exists inside Q, hidden inside Q. So it is called the existential quantified type. So this is a type notation that I would use to denote this definition. This definition is a type constructor with parameter a, which inside hides type z, which must exist. So to build a value of this type, we need to find some type or select some type z, put it in, put a value of this type in there, but we hide it. So outside we don't see that z, it exists inside. So this is the notation, and this is called the existential quantifier. So this existential quantifier basically says that this constructor, it has this type. So the function qz constructs a value of q of a, so it hides z. It's a very interesting thing. So the syntax says that qz is parameterized by both a and z, but the role is very different for a and for z. The role for z is existentially quantified because it's hidden from the outside. The role of a is a type parameter visible from outside, and the functor in a. So this is obviously a functor in a. It is not universally quantified. So even though it's a type parameter here, it's not universally quantified with respect to z. And this is so because when you build up a value of this type, you must use a specific z. It will not work for another z later. It will have that specific z baked in the value q once you construct it. So that's why it is an existential quantifier and not a universal quantifier. But the code does not show this explicitly. The code is a bit confusing. We have just seen a universal quantifier in the code here and here. And the way to implement this universal quantifier was to have a method inside a trait, and the method was parameterized by this x. The way to have an existential quantifier is to have a case class inside the trait, and the case class is parameterized by this z. The method inside the trait hides the x because the x is not a parameter here. The case class inside the trait hides the z because the z is not the parameter here. So until now it's very similar, but case class is not a method of a trait. So this is the crucial difference. So if it's a method of a trait, then it would be a universal quantifier, a method that has an extra parameter hidden from the outside. A case class with an extra parameter hidden from the outside, that represents the existential quantifier. So we have to keep track of this ourselves. The syntax of Scala does not help so much to keep track of this. But this is a very significant difference between the types.